discussion on nuclear physics, then we will come back to doubts and questions. So nuclear physics, we had talked about basic structure of the nucleus in terms of nucleons and the concept of mass defect and binding energy of a nucleus in terms of mass defect. And from that we had discussed about stability of the nucleus depending on the quantity binding energy per nucleon. So we had seen that if a nucleus consists of z number of protons plus a minus z number of neutrons and has a mass m, then the binding energy of the nucleus becomes the mass defect, that is mass of the constituents minus the actual mass into c square, and therefore binding energy per nucleon becomes this thing, binding energy divided by the number of nucleons. Okay. And this is the quantity which tells us about stability of the nucleus. The larger the binding energy per nucleon, okay, more the stability. So in this regard, what happens is that nuclear reactions typically tend to happen in such a way that the daughter nuclei are more stable compared to the parent nuclei. So nuclei of lower mass number tend to fuse into heavier nuclei of larger E and greater stability. Okay. For example, let's say a hydrogen nucleus plus a deuterium nucleus. Okay. Or let's say a tritium nucleus plus a hydrogen nucleus might fuse to give you a alpha particle or a helium nucleus plus a neutron. So this is an example of a fusion, nuclear fusion reaction. Whereas heavier nuclei tend to break into lighter, more stable nuclei by a process called nuclear fission. So these are typical type of situations in which nuclear reactions happen, and typical type of nuclear reactions, fission and fusion, are two the standard type of nuclear reactions. So you can just make a note of this part, we'll discuss more. Yes, that is true, Sudhir. So, like fusion reactions are partly, I mean, the most common fusion reactions, like the one example I've shown you, happen in the core of stars. So they are conditions of high pressure and temperature. Okay. So, okay. So typical example of fission reaction would be something like this: uranium 236 isotope, highly fissionable, and it undergoes fission into okay, and also another type of reaction that can happen is this. In fact, this is the more common one. Same isotope of uranium 236. Okay. By the way, uranium 236 does not exist a lot in nature, so it has to be created from uranium 235 by bombarding it with slow moving neutrons. Anyway, this barium plus krypton one is more common in nuclear fission reactors. Krypton 36. Okay. The thing is, you don't have to memorize any of these reactions, etc. What you have to be able to do is the calculations from the reactions. So you can do a bit of reading work about both fission and fusion reactions from either NCRT or HCV, which will be beneficial for your board also. Okay, you can read about fission reactors also, okay, or nuclear power plants. What is basically you can read about solar fusion reactions, okay, which are typical fusion reactions that occur in the core of stars. Like our sun. And that all will contribute towards your general knowledge also. Okay. Then there are some other types of reactions like breeder reactions, things like that. So another example of a breeder reaction is uranium 238, which is the isotope of uranium that exists in maximum percentage in a natural sample of uranium, is bombarded with neutron, and it absorbs the neutron but in a very high energy state. So immediately it then undergoes fusion, fission, and it ultimately gives, okay, plutonium, which is very reactive. So this this plutonium is an example of nuclear fuel. Because it's not naturally occurring isotope of plutonium. Yes, that is the point. Uranium 238 is the abundant, more than 99 point something percent of all uranium deposits have that uranium 238 this thing isotope. And therefore, it is not that reactive. Whereas uranium 235 is the one which is, you know, uranium 235 is the one which is also available in natural samples of uranium, but in much less percentage. So this is actually created by bombarding the 235 isotope with a neutron, slow moving neutron. So it goes to this state. And in the process, of course, you can see that it emits two neutrons. So it becomes a chain reaction. So any natural sample of uranium will have these two isotopes, 235 and 238. Okay. This is in very high percentage. This is in lesser percentage. Okay. So basically, this process we say that this 235 uranium sample is made fissionable, okay, by bombarding it with slow moving neutrons, which then undergo, which gives you the uranium 236 this thing, no, isotope, which is highly fissionable. So this is the process in nuclear fission reactors. Yeah. So there are many different types of nuclear reactions, and there is a lot of information you can get about nuclear reactions of these two types, particularly fission and fusion. And in fission also, the nuclear fission reactor type, uranium fission reactor type of reactions, and solar fusion type of reactions, which you can go through from any standard textbook. But from our point of view, what is important is to understand the conservation principles in any nuclear reactions. Okay. And then later to understand the kinetics, the reaction kinetics. So conservation principles in a nuclear reaction. So we can look at a most general type of nuclear reaction, where what is happening is that we have, let us say, a target nucleus, okay, which is the unstable one. Okay. So this has, let us say, certain mass number and certain atomic number. Now, in order to initiate the reaction, it is hit by an initiator, which is a small particle collided with the target. So examples of this could be like alpha particle, hydrogen nucleus, neutron, etc. Now, as the nuclear reaction happens, it gives us a product nucleus, which has, let's say, which is more stable, which might have some kind of speed or velocity. This one is typically at rest. Some kind of outgoing particle, so again examples of this would be neutrons, protons, etc. and photon or photons. Okay. And typically this would be photons of energy very high, of the order of giga electron volts. So they are in the gamma radiation region. So this is the scheme of a typical nuclear reaction. Now in certain reactions there won't be any initiator, certain reactions there won't be outgoing particles, or they might not be photon. Okay. So it depends, but this is like a general scheme of things. So in any nuclear reaction which has a maximum of these many, you can say, um, these many characters that are part of the reaction, the quantity is conserved. First of all, number of total number of nucleons, okay, and charge, both the things are conserved. In fact, you can write them separately also, it doesn't matter. Total number of nucleons, that is number of neutrons plus protons, okay, that is conserved, and charge is conserved. Now mind you, as far as charge is concerned, you can have an outgoing particle like an electron or a positron also, which is the antiparticle of an electron. So it would not count in number of nucleons, but it would count for charge. If your outgoing particle consists of electrons or positrons, they will contribute to the conservation of charge, but they will not be counted in the number of nucleons. Nucleons is number of neutrons plus protons. Okay. Now the next thing that is conserved, is very important, is linear momentum. Okay. So in the reaction that I've shown above, Typically, it is the linear momentum of the initiator which must equal to the total linear momentum, that is the vector sum of the linear momentum of the product nucleus, the outgoing particle, and the this thing photon. An outgoing particle and photon might be multiple in number also. And now the most important thing which is conserved, which is mass energy is conserved. Okay. So from the conservation of mass energy only, we will understand what is called the Q value of the nuclear reaction, or the energy liberated per reaction. So let us understand this conservation of mass energy. So what is happening there is our initiator plus target nucleus is giving us a product plus outgoing particle plus photon. Okay. So this was at rest to begin with. Okay. This was moving at V1. This was moving at Vp. This was also moving at Vo. Okay. And this of course has an energy equal to hc by lambda. So conservation of mass energy this basically means that the total energy, that is including the rest mass energy, okay, of reactants and products are equal. Okay. So aside from this, as we had learned last time, that when we write E is equal to mc square, where m is the dynamic mass, we can approximate this as m naught c square plus half m naught v square, where v by c should be very small compared to 1. Okay. So this is what we'll write as the total energy of a particle which has a rest mass of m naught and which is moving with a speed v. So over here we will have, when we apply conservation of rest mass, sorry, when we write conservation of mass energy, for the initiator we will have this much rest mass energy plus this much kinetic energy. For the target nucleus we will have this much energy because it was at rest, so it has only rest mass energy. For the product nucleus we will have rest mass energy plus kinetic energy. Okay. For the outgoing particle we will have again rest mass energy plus kinetic energy. Okay. And for the photon we have hc by lambda. So this is equal to, because so this is the conservation of rest mass energy. Now from this you can see that if we define Q value of the reaction as the energy liberated, that is kinetic energy of product plus kinetic energy of outgoing particle plus energy of radiation. Okay. But of course minus the kinetic energy of the initiator, this quantity. So that Q value of the reaction is nothing but this thing. Okay. So this quantity is the Q value. So from the above reaction, you can easily see from conservation of mass energy, you can see that the Q value, which is this quantity, can also be expressed in terms of mass defect. This quantity, or the Q value, which is kinetic energy of products plus photon energy or radiation energy minus kinetic energy of reactants. This is actually equal to mass defect. So this is the single most important concept in calculation of energetics of nuclear reaction. Okay. So just go through this conservation principles and make sure this is clear. So any calculation we are doing with respect to a nuclear reaction, from Q value of the reaction to certain unknown values in it, etc. Anything will be solved by using one or more of the conservation principles. There is anything to do with the timeline, the kinetics of the reaction, that will have to do with the disintegration law, which we'll come to later. Yes, with the I'll scroll down. Okay, so let's look at a typical example question. Okay, so we have some isotope of plutonium which is undergoing a fission reaction to give some particular unknown product nucleus plus an alpha particle. Okay. You know that alpha particle is basically a helium nucleus. Okay. So anyway, so first of all, find A, the isotope of plutonium. Okay. Find Z and identify X. Okay. And third, given the mass of the nuclei or masses of the nuclei, for plutonium the mass is 238.0496 atomic mass units. For the unknown product nucleus, it is measured to be 234.041 atomic mass units, and for the helium nucleus or the alpha particle, the mass is 4.0026 atomic mass units. Okay, so given this, calculate the Q value of the reaction, okay, and the alpha particles kinetic energy. Okay, assume the plutonium nucleus was at rest. Yes, correct. Uranium is the correct answer, 92, and E is 238. That's correct. So basically, you can just see that all you have to do is you have to add up the numbers. So plutonium E94 is giving you X Z mass number 234 plus helium nucleus 2He4. Okay. So conservation of nucleons. That will be the first thing. So A should be equal to 234 plus 4. So that is 238. Okay. So A is equal to 238. Is the 238 isotope of plutonium. And secondly, conservation of charge. Okay, so 94 should be equal to the sum of Z plus 2. So Z should be equal to 92. So that means it's nothing but uranium. And next thing you have to do, Q value, that will be equal to mass defect into C square. So that is the mass of the uranium 230, sorry, the reactant, that is minus this converted into energy. Okay, so you can see that will become okay. So now you use that standard unit, that one atomic mass unit into C square is 931 million electron volts. So this will come approximately 5.6 million electron volts. Okay. In modern physics, we use always electron volts unit for energy, not joules, unless specifically mentioned in the question that calculate in joules. Okay, now about the kinetic energy of the alpha particle, one has to understand one thing over here, that the plutonium is breaking into uranium plus alpha particle, so they must be moving in opposite directions because the momentum is zero. Okay, so mass of uranium, so basically mass of uranium into V prime must be equal to mass of alpha particle into V, which is P, suppose. Okay, so this is conservation of linear momentum. Okay. And kinetic energy of uranium plus kinetic energy of the alpha particle, that is the Q value of the reaction. This is conservation of mass energy. Okay, so this can be written as P square by 2 times plus P square by 2 times mass of alpha particle. It can be written more conveniently like this. So P square by 2 into 1 by 234 plus 1 by uh, 4 is equal to Q. This is in atomic mass units. Okay. And or we can just calculate it like this. We know that the sum of the kinetic energies is equal to 5.6 million electron volts, and since the momentum is equal, okay, so 234 V prime is equal to 4 V. So V prime is 4 upon 234 times V. Okay. So kinetic energy of U is half of mu into V prime square. So that is alpha particle. So the kinetic energy of this, actually a very small fraction, that is approximately 58.5. So this we can use. Okay. This is the easier thing to use. Use this over here. So kinetic energy of alpha particle into 1 upon 58.5 plus 1 is equal to 5.6 million electron. So it's nearly the same because this is very small. But nonetheless, there is a technical difference between the two. This is slightly less than 5.6 million electrons. So typically this is what happens when you apply the momentum conservation. The target nucleus is so much larger in mass that it has very little amount of kinetic energy. Yeah, something like that. This will be something of the order of 5.5 million molecules. Okay. So if you missed out this point and there are two options which are 5.6 and 5.5, then you'll get the wrong answer here. So it is very important to be this thing. Okay, so hope this is clear. So people will take a quick break. This completes the Q value part of nuclear reactions, or the reaction part of nuclear physics. Now next we will look at the kinetics of nuclear reactions, the rate of reactions through the disintegration law. So basically it's very simple, but there's one case of chain reaction where we have to understand how to solve a linear differential equation to find the kind of kinetics involved. Otherwise, mostly it's first order disintegration that you're familiar with chemistry also. So you just have that normal relationship between half-life and disintegration constant. That part is very easy. So that will just take a bit of time, and then we can maybe discuss some questions in wave optics which you have sent us doubts earlier. Yeah. So just take a 5-10 minute break. We'll continue after that. Okay, people, let us restart. So next we will discuss about kinetics of nuclear disintegration. So typical examples of nuclear disintegration are alpha decays, beta decays. These are what we call natural decay reactions. Oh, sorry, this one will be, yeah, this Z plus one was correct, but this one will be an example of. So just an interesting fact that whenever in a nuclear reaction a positron is produced, it immediately annihilates with an electron to produce a pair of photons. Now, why always it produces a pair of photons is because of momentum conservation. So this is not important from your syllabus point of view, but it's just An interesting fact, you might be wondering why positrons don't exist, as part of the nuclear particles or atomic particles, is because positrons don't exist for too long. Their lifetime is very short. Positrons have extremely short lifetimes because on being emitted in a beta plus decay or any other nuclear reaction, almost immediately a positron and electron pair annihilate. Annihilate means they get destroyed, they vanish, producing a pair of photons. Now, always it is a pair of photons, so that the net momentum is zero. That's why it be a pair of photons and not a single photon. Anyway, now coming back to the kinetics, the rate of disintegration, that is what we call number of disintegrations per second, that is number of nuclei undergoing spontaneous natural disintegration in a radioactive sample. So that is given by the rate law. Number of disintegrations per second or rate of disintegration is equal to lambda into n. This is the rate law for spontaneous decay reactions, okay, where n is the number of nuclei, okay, in the radioactive sample, and lambda is called the disintegration constant, as you know. Expressed in second inverse. So a simple integration of this tells you that at t equal to 0, if the number of radioactive nuclei was n naught, then the instantaneous number n is given by this, okay, and at t equal to t half, n becomes half of n naught. or T equal to 2 times T half. Not think of this as T by 2. So on and so forth. So in general, in n half-lives, the number of samples becomes, or number of nuclei becomes this. Okay. So this is a very simple calculation which comes from the fact that n naught by 2 is equal to n naught e raised power minus lambda into half-life. So from this you can see that. So again, this is experimentally observed. There is no particular theoretical derivation of this disintegration law. So let's look at an example. By a certain industrial process, okay, nuclei of a radioactive isotope are produced at a constant rate of P per second. There's a production rate P per second. Now, this sample has a disintegration constant of lambda. Assuming T equal to 0, when the production started, N naught was 0, that is the initial number of nuclei was 0. So calculate N as a function of time and N after a very long time. that is time very large compared to 1 by lambda. Assume the rate of production is constant. Yes, very good, Ganesh. That's correct. Somadeep, your answer is also correct. Samyak, your answer is correct. So this is basically just solving a differential equation. So what will happen is that at t equal to 0, n naught is equal to 0. So at some time t, if n is equal to n, then dn by dt will be minus lambda n plus p. Okay, because dn by dt will equal to the rate of decay or rate of production minus the rate of decay. Okay, so that is p minus, I mean, this is the thing. The rate of change, the net rate of change, you can say, that will be equal to this. Okay, so we have to use that as a boundary value and just solve this. So minus 1 by lambda ln p minus lambda n is equal to t. Because this is going from 0 to n. So ln p minus lambda n upon p is equal to minus lambda t. This kind of thing we'll get. So for t very much larger than 1 by lambda, lambda t is very large. So e raised power minus lambda t is tending to 0. So n tends to a steady state value as t tends to infinity. Basically, t is extremely large compared to 1 by lambda. This is so very simple question, as you can see. It's just solving of differential equation. Okay, so hope this is clear. Now next term we'll understand something called average life. So average life is, like a statistically determined kind of term. Like, to understand average life, you can start by understanding that what is happening is that you start out at t equal to 0 with very large number of samples of radioactive materials. By the time you come to half life, you have half of them left. By the time you come to 2 times half life, you have 1/4 of them left. So for 50% of the nuclei, okay, the lifespan is less than t half. Okay, so that their life expectancy is anything between 0 and t half. For 75%, their lifespan is less than 2 times half life. Okay, and like that, if you go on taking a bigger amount of time, the percentage of nuclei which have decayed within that time goes on increasing. So average life is a sort of average life expectancy for a random nucleus. If you pick up a nucleus at the beginning of the experiment or when you're starting your time calculation, then what can you say on an average is the life expectancy of that? Okay? So that quantity. So that is given by a simple formula. I'll tell you the process of calculation of that formula also. And that process is nothing but 1 by lambda, or half life upon 0.693, or you can also write it as half life upon ln2. Now the process of this calculation is a little bit more involved, so you have to understand how we come to this conclusion. So suppose at t equal to t, n is equal to n, which we know is n naught e raised by minus lambda t. Okay. And at t plus dt, this has become n minus, okay, where this this is the number of nuclei decayed in the small time dt between t equal to t plus dt. So what is happening is that for this dn number of nuclei, for these many number of nuclei, the lifespan was equal to t, because t to t plus dt is a very small time. So you can say that all the nuclei that have decayed within this time and t plus dt, they have had a lifespan of t. Okay. So now to calculate the sum of all the lives of n nuclei. Okay. So from t equal to 0 onwards, for all nuclei that are active, that means which have not disintegrated, okay, the sum of the lives, the sum of lifespans, that is summation ti for all of this. Okay, you can think of that as s. So that is nothing but integration of tdn. Okay. Why it is like this? Let's understand. So if T1 was the lifespan for N1 number of nuclei, then T2 was the lifespan for N2 number of nuclei, T3 was the lifespan for N3 number of nuclei, like this. Then the total life S would have been N1 T1 plus N2 T2 plus N3 T3. So it would have been summation of Pi Ni, okay, where this is the life span for these many number of nuclei. So the total of sum of all lifespans for all nuclei. Okay, this thing actually we would have treated it like this, summation niti. That quantity is tdn integration, because dn number of samples had a life of t. So now we integrate by summation this thing. So now put this value here. Okay. So you can see that this becomes this quantity. Okay, from 0 to infinity, because now we are integrating with respect to time. So the complete disintegration is over at t tending to infinity. So do these steps of integration. There is that you'll have to use the integration by parts kind of method. Just a second, I'm missing some term. There should be a lambda also somewhere. There is a lambda here now. There is an extra term of lambda because dn by dt is n lambda. So is the mod of dn by dt is n lambda, and that is n naught e raised by minus lambda t into lambda. So there's an extra lambda term here. So basically this dn is lambda n dt, which is like this. Yeah, so there is an extra lambda term here. You just plug it in. So we can actually first write this as t into lambda n dt, and then further write the n like that. Like so. So this is going from t equal to 0 to t tending to infinity. So integration by parts will be required, as you can see. But you people are experts in integration, so I'll leave you to do all the steps. And this comes out to be n naught by lambda. So this is basically what it is, the sum of all lifetimes for the entire sample of n naught active nuclei at time t equal to 0. Okay. So therefore average life, that is going to be this sum divided by the number of nuclei. So that's how we get the average life as 1 by lambda, which is the same thing as half life by ln2. Okay, so anyway, I don't think this derivation is important for your board's point of view. Okay, and definitely derivation is not important from JE point of view. So I've given you the derivation for your understanding of this, because it's a statistical quantity, the average life. For an exponentially decaying sample, you are interpreting this thing. So basically, if you think about it, your number of nuclei versus time graph is like this. So see, this was the quantity that we calculated, that at a particular time between t and t plus dt, dn number of samples were getting disintegrated. So this quantity was our tdn, because this was our dn. Okay. So when we calculated integration of tdn, we are basically calculating the area under the curve, which is giving you the total lifespan of this is S. The sum of lifespans. Okay, next thing we will understand is activity of a radioactive sample. So this is actually something very simple. This. Okay. So as you can see that n being n naught e raised power minus lambda t, dn by dt is minus lambda n naught e raised power minus lambda t. So the activity becomes lambda n naught e raised power minus lambda t, or we can say that the activity is e naught e raised power minus lambda t, where e naught equal to lambda n naught is the initial activity at t equal to 0. So the activity graph follows the same kind of profile as the number of sample graphs follows. It, activity also decays in the same way. Okay, next, chain disintegration. So suppose we have, so this is an unstable or radioactive element which first decays into another unstable species and finally into C, which is a stable species. Yes, Aditya, I'll give it. Just a minute. Back to this. Yeah. So now let us say at t equal to 0, number of samples of A was n naught, number of samples of B and C was 0. Then calculate NB and NC as functions of time. Okay. Calculate the maximum of NB for any time greater than 0. Okay. So this just basically becomes a standard sort of exercise in differential equation solving. So for E, what is happening is you have, okay, and Na equal to n naught at t equal to c. So this is a very simple solution. Na will become n naught e raised power minus lambda 1 t. That's the first thing. Okay. But for B, what is happening? For B, this quantity is the rate of production minus the rate of disintegration. Okay. And the rate of production of B is basically equal to the activity of E, which is, okay, so that is lambda 1 n naught e raised power minus lambda 1 t. So we have this differential equation. So this is how we end up with what we call a linear differential equation. Yes, you would have done linear differential equations in mathematics by now as part of the chapter differential equations. So this is a linear differential equation of the type. Okay. So the method of solving this, we define something called integrating factor as this. Okay. Then we multiply both sides with the integrating factor. Okay. And then we integrate both the sides with respect to x. So this term actually becomes y into integrating factor. As you can see, the derivative of this is this. So this is how we solve the differential equation. So here you can see that this is your dy by dx kind of term. Q kind of term. So your p is actually a constant, lambda 2 minus lambda 2. Y is nd and x is time. Sorry, plus, no? Yeah, my mistake. So in this case, your function px is actually a constant. So your integrating factor e raised power integration p dx just becomes e raised power lambda 2 dt. You might say that we'll add a constant term, but that just adds a constant here, so we resolve that in the final constant. So when you take integrating factor into LHS is equal to integrating factor into RHS, this here becomes integrating factor into y, this step. So y की जगह क्या है अपने पास nb. So nb into integrating factor is equal to integration of the left hand side, sorry, right hand side into the integrating factor. So e raised power lambda 2 multiplied with lambda 1 n naught e raised power minus lambda 1 t dt. So nb e raised power lambda 2 t becomes lambda n naught into integration of e raised power lambda 2 minus lambda 1 t dt. Now we will introduce the constant of integration also and be able to remove from our analysis This kind of term we are getting. Okay. We can also see that NB is equal to 0 at t equal to 0. Therefore, the constant has to be minus lambda 1 upon lambda 2 minus lambda. So with that, NB as a function of time just becomes okay. We can write it like this for lambda 2 greater than lambda 1, or we- or lambda 1 greater than lambda 2. So whichever way we write it, this, if you apply maxima concept and all that, see it has like this. So eventually it decays to 0, but it has a maxima at some time in between. So that also we'll calculate. Okay. But first you note down this entire analysis. This is something which is not necessarily explained very well in all reference books. Okay, so hope this is clear. Now, once we figured out NB as a function of time, we can also see about NC at any instant of time t. Na plus Nb plus Nc should be equal to N naught. Okay. That was coming from the decay reaction. Okay. So this was N naught at t equal to 0, and these two were 0 and 0. At some time t, this is Na, Nb, and Nc. So their sum should be equal to the original number of N naught. So that's one very easy way of calculating Nc. It is N naught minus Na plus Nb. So that is this kind of term. So we should come with plus. So this has that interesting character that but Nc tends to become N naught as t tends to infinity. Alright, that's about that. Now to find the maxima of this, or NB's maxima, it will occur at the time when the slope of NB versus time becomes 0. And that happens only once. Here you can see the slope dn by dt should be 0. So it occurs at t equal to this, let's say when, okay. So if you differentiate this and put it equal to 0, you'll get This is if lambda 2 is greater than lambda 1. This is if lambda 1 is greater than lambda 2. So it occurs at this kind of time. Okay. So this is our T max. But you can also see that at this time you can replace this term like this. So this second term just become lambda 1 by lambda 2 e raised power minus lambda 1 t. Substitute this. Again, you will get some special kind of value here. So that will become some term like this. It becomes. So this becomes 1 plus lambda 1 upon lambda 2 minus lambda 1. So that becomes lambda 2 upon. And something like this. But anyway, this is something which is a numerical value you can calculate if required in some question. The important thing is how you come to the conclusion of the maxima. Okay, so people will have to conclude today's lecture here. Uh, Aditya, I'll pick up your doubts in wave optics in the next session. Also, a couple of doubts that you have asked towards the end, they are to do with something called Rayleigh criteria, which is diffraction through a circular aperture, which I will discuss with you when we are doing about polarization and optical instruments, because that part is again to do with JE mains only. Okay. Interference due to thin films you can solve yourself using the optical path length concept. But the last couple of questions in HC were, I think, 40 and 41 or whatever, 41 and 42. They have to do with another formula which I will be discussing with you during optical instruments. So don't worry about those two questions. Okay. So we'll conclude our session here today. Okay. With that, we complete modern physics for JE Advanced and Mains. Now, the topics that are remaining in my track are the exclusive JE Mains only topics, namely polarization of light, optical instruments, and then semiconductors and logic gates in modern physics. So we will discuss them in this order only. So while doing polarization and optical instruments, we will also pick up the wave optics doubts that you have.